Welcome to the lecture on vibration measuring instruments. So, we have discussed about vibrometers, about accelerometers, about velocity pickup or velometer, and we saw that with these instruments, when we discussed, we were talking about the amplitude, but there was not a proper discussion on phase. But here now I would discuss the importance of phase in measuring the in the measurement of the vibration through these instruments. So we can see that we have some again this structure. So this is vibrating structure, and it is y equal to y sine omega t. Now we have this seismic mass m k c, and this is the frame of the instrument, and this is z, and we say that z equal to z sine omega t minus phi. So here phi is the phase lag. It means that if I have this motion y, this is y, that is y equal to y sine omega t, and I measure the relative this z, so it will have some phase lag, means so it will start something like this. Okay, and so there is some, we can say, time lag, or also this is t, and t equal to phi upon omega. This is time lag. So also we can see another example. So here we have, so if we have a single harmonic excitation, we have no problem, because my signal is shifted. I mean, there is some phase lag. If I shift this signal with that constant phase, I can start it, and I can follow the y. Right. But if the signal contains more than one harmonic, for example, we can see the figure, and here we have like input signal, that is y. So this is sine omega t. So y here is sine omega t and plus sine 3 omega t. So this is, there are two sine functions, sine omega t and sine 3 omega t, and their resultant is coming. So it is, we can see that it is combination, the combined signal, it is also starting from 0. However, when we see, so it is like a1 sine omega t and a2 sine 3 omega t. Now if we get the output and we plot the output, and there is some phase lag. So if we get z, and it is z1, here we can say this is y1 and this is y2. So here z1 and sine omega t minus phi 1, there will be some phase lag, and plus z2 sine omega t minus some other phase lag phi 2. It is 3 omega t minus phi 2. So there will be some phase lag for both the signals. So now let us say phi 1 equal to 90 degree and phi 2 equal to 180 degree, because this phase difference will be different, and so if the phi 1 is 90 and phi 2 is 180 degree, we will have Z equal to Z1 sin omega t minus 90 degree plus Z2 sin 3 omega t minus 180 degree. Now if we plot these signals and their resultant we try to obtain, and so we can see that one signal is this. So it is starting with some phase minus 90, so it is starting like this, and the second signal has phase of minus 180 degree, so it is starting something like this, and the resultant of these signals will be something okay. So this is a distorted signal. This is a distorted signal. So when there is due to this phase lag and if there are signals more than one harmonic, and because they are subjected to different amount of phase lag, and when they are sum up, the resultant signal gets distorted, and that is what we call phase distortion or phase shift error. Now how to minimize or these errors in case of vibration pickups like vibrometers, velometers and accelerometers. So let us first discuss the vibrometer. So these things we can understand with the help of the phase plot phi and r. So this is the phase plot, and this phase plot is like this. So this could be zeta equal to 0.3, this is 0.5, this is 0.7, then this could be 1 and so on. Okay. So 1.7, 0.5, 0.3, and this is zeta equal to 0, this is zeta equal to 0, this is zeta equal to 0. So this is the phase plot or phase response curve for the vibrometers. So we see that if we have signals like this and phi 1, so phi 1 equal to tan inverse 2 zeta r by 1 minus r square, and this phase, because for the vibrometer, in case of vibrometer we have r much greater than 1. Okay, so we are in this r much greater than 1 range. So if it is, this is z by y, and we have, this is r equal to 1 and 2 and 3, and this is 1 and 2. So we are in this range. So we are beyond this range. So r is much greater than 1 or r is greater than 3 for the vibrometer. So for vibrometer r is greater than 3. So therefore, if we want to solve the case of phase distortion in case of vibrometer, we must select R such that the each signal has the phase phi that is equal to 180 degree, and this is possible when zeta is 0. So if we keep damping very small or near 0, so we will get the phase, the constant phase lag for each signal, and so all the signals can start from the same point, and when they are added, the resultant will be the will not be distorted, but it will be the correct waveform. Although due to the 180 degree phase it could be negative, so here let's do like this. So if we have phi 1 equal to 180 degree and phi 2 equal to 180 degree, then what will happen? So z equal to z1 sin omega t minus 180 degree plus z2 sin 3 omega t minus 180 degree. So it is minus z1 sin omega t, and this is minus z2 sin 3 omega t, and so it is minus z1 sin omega t plus z2 sin 3 omega t. And because we select such condition r much greater than 1, that z1 is about y1 and z2 is approximately y2. So we will get this z is approximately y is approximately y1 sin omega t plus y2 sin 3 omega t. So we are getting this same response as the vibration of the structure, only there is minus sign, means if the one response is starting like this, the other one will start like this, and easily we can change the direction of this waveform, and so we can get the correct one. Okay. So the in case of vibrometers and case of velometer, because velometer follows the similar condition as the vibrometer, because in also in velometer we take R much greater than 1. So both for vibrometer and velometer, if we want to avoid the phase distortion, we have to select the value of R much greater than 1 and the value of damping that is near about 0. So the phase lag is constant for each input, and it is constant, that is 180 degree. Now what happens to accelerometers? As we know that accelerometers, they are widely used and their operating ranges are much less than 1. So for accelerometers r is much less than 1, and so in this case we can't avoid to have like phase 180 degree, we can't have. Now suppose the excitation, the vibration has higher harmonics. Okay, so it is non-harmonic function, or if it is a periodic function, so it will contain several higher harmonic. Okay, because the Fourier series, according to Fourier series, we can break a periodic signal into harmonic signal containing several higher frequencies, or the signal has several of higher harmonics. Then what we will do? So let's assume that my signal, so this is my input, so this is AI, this is A1 sine omega t plus A2 sine 2 omega t plus A3 sine 3 omega t plus. So it may contain the harmonics. So this is fundamental harmonic, this is second harmonic, third harmonic, and so on. Now my output acceleration will have something, let us say it is B1 sine omega t minus phi 1 plus B2 sine omega t. Now here we assume that we are making our accelerometer such that it is following the amplitude correctly. So we are going to have the same amplitude as A1, because as we said, we discussed that we design our instruments like vibration pickup such that they closely follow the vibration response. So the relative response follows the closely the input or vibration response. So it is amplitude is okay, we are getting A1, A2, but we are getting this phase shift. So it is omega 2 t minus phi 2 plus A3 sine 3 omega t minus phi 3 plus and so on. So if we have these shifted, so all these signals, if we plot, they will be, I mean if this is so they are shifted. So and so if you get the resultant, that will be something very illogical. I mean we can't if we combine, we can't get the exact input or close input signal. So therefore now what we will do, so as we discussed that in case of accelerometers we usually keep the value of damping zeta equal to 0.7. So we keep zeta equal to close to 0.7 or little lower. Why do we keep zeta equal to 0.7? Because that parabolic curve that follows in that range are much less than 1, the other curves that is zeta equal to 0.7. And if we see the phase lag or phase curve, so we see that for in case of phase curve, for zeta equal to 0.7 in this range, this is linear. So this is approximately linear, this curve for zeta equal to 0.7. And so if I have here we have this r is equal to omega by omega n. Okay, so for here it is 2 omega 2, so it is sine 2 omega t and 3 omega t. So if it is omega, we will have here phi 1. If it is 2 omega, we will have phi 2. If it is 3 omega, we will have phi 3. Now because this curve is linear, this is linear, so for each omega, so for omega it is phi, then for 2 omega it is, the phase is 2 phi because there is linear relation, and for 3 omega it is 3 phi. So it means that my phi is equal, phi 1 is phi, then phi 2 is 2 phi, and phi 3 is 3 phi, and so on. So we are getting a linear relationship in phase with the harmonics, the frequencies, higher frequencies. So we can write output equation A0t equal to A1 sine omega t minus phi plus A2 sine 2 omega t minus 2 phi plus A3 sine 3 omega t minus 3 phi plus so on. Now if we take omega t minus phi equal to beta, so we can write A O t, so we can write A O t, that is equal to A1 sine beta plus A2 sine 2 beta plus A3 sine 3 beta plus so on. So what we see that now here is no problem of phase lag. We have solved that problem of the phase lag, and my signals can all start with 0, omega t minus phi equal to 0. So we have solved this phase problem. So in case of these accelerometers, we can take zeta equal to 0.7, and this will solve the problem of phase. Now we come for frequency measurement. As we have some time, we have to measure the frequencies. So for frequency measurement, we use one instrument that is known as single reed instrument or full Orton tachometer. So here this single reed instrument is, we have this instrument, and so we are going to attach this instrument with this vibrating body. So this is my vibrating body, and we attach this instrument here. Now what is the property of this instrument? That it is like a cantilever beam. So it is a free end cantilever beam where at the end there is a small mass. Now you know that for a cantilever beam, omega n, that is equal to root k by m, and k is so k depends on length. Okay, so k is inversely proportional to length, and so here by it means that by changing the length of the cantilever, we can change the natural frequency of that cantilever. So here there is a screw, so this is a screw, we can screw here and we can vary the length. So, if we want to measure the frequency of vibrating structure, we attach this instrument with that structure, and of course we know that what is the range of the frequency of this cantilever and what is the possible range of the frequency of that structure. Now we keep on changing the length of that cantilever, okay, and we see that at which length the mass of the cantilever vibrates with the large amplitude, because that is the resonance condition. If my structure is vibrating with, it is vibrating with omega, and we are changing a length, and at certain length this is vibrating with very large amplitude, it means this omega is equal to the omega n of this cantilever. So, and we know that omega n because we know all the properties of this cantilever, and so we know the omega n, it means that is the frequency of the omega, because at resonance we know that omega equal to omega n. Okay. Now we have another instrument that is called multi-reed instrument or Fram tachometer. The principle is same also for this instrument. However, there are several cantilevers, a set of cantilevers, so a wide range of frequencies are possible, and in this range we can see that the mass which has the close frequency to the structural structure vibration, that mass will vibrate, other masses will be not vibrating with that much amplitude. So, from here we can know that what is the frequency of the structure close to the omega n of that particular cantilever, and so we can get the natural frequency, the vibrating frequency of the structure. So, I stop and we complete the vibration measurements, and I thank you for attending this lecture, and see you in the next lecture. Thank you.